Hi everyone. In this video we're going to continue our look into solving trigonometric equations and finding all solutions. So let's get right to it. In this particular case for this example, the algebra will be identical to whether the tangent was there or not. In this particular case, I think we can all see that we're going to add 1 and then take the square root. Right? So we're going to do that same thing, but with just a tangent there. So the algebraic portion of things are, the algebraic portion of this is really identical to whether or not the tangent was there. So in this particular case, we'll get the tangent of x equals, don't forget, the plus and minus 1. Okay, the plus and minus comes from that square rooting in solving. So, excuse me, what we want to consider is where is tangent 1, right? So let's go back into our memory banks. Remember that we have sine and cosine as our coordinates. We remember that the tangent is the sine over the cosine. So in order to get a tangent of 1, the sine has to equal the cosine. So where are the values on the unit circle where sine is equal to cosine? Well, that would be right here. That would be right here. But remember, we have plus and minus 1, so we can have any combination of positives and negatives in this particular instance. So we also have these two. So all of the 4 denominators, all of the pi's over 4. So what we have is, straight up solving this for x from the unit circle, we get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But once again, we want to find all solutions, and that means we do need to include coterminals. All right, so we're going to set up our coordinate plane. We're going to sketch our 4 angles. We've got pi over 4, we've got 3 pi over 4, we've got 5 pi over 4, and 7. And you could make it simple. You could say that all of the solutions are, you could say pi over 4 plus 2n pi, where you're adding 1 revolution, or adding 2 revolutions, or adding 3 revolutions, right? That would be that. And you could say 3 pi over 4 plus 2n pi. In other words, 1 revolution and 2 revolutions and 3 revolutions, right? Any multiples of 2 pi would be adding revolutions. And you could take that current trend, 2n pi, and 7 pi over 4 plus 2n pi, where, remember, n is an integer. Or you could think it through a little bit and say, all right, can I get from one solution to the next in a consistent way? So for instance, up here in purple, we could get from one solution to the next by adding a multiple of pi each time, rather than just saying, adding a full revolution to each. So can I get from pi over 4 to 3 pi over 4? Yeah, sure I can. This would be a 90-degree rotation, right? Pi over 2. Can I get from here to here? Of course I can. This is also pi over 2. Pi over 2. Pi over 2, right? So in other words, what we can think of is, for all solutions to this equation, we've got pi over 4, which is our first answer, I just erased rather than highlighted. We've got pi over 4, which was our smallest unit circle angle that solves this equation, plus, well, any multiple of 90 degrees, right? So n pi over 2. So we could rotate any number of 90-degree multiples to generate a new solution to this. And again, we have to define that n is an integer. In class, we're going to define a a different type of notation for this thing, which we'll formalize in class. But basically what this looks like is x is equal to, we'll put it in set notation, pi over 4 plus n pi over 2, and then we're going to get this set builder notation, meaning such that n is an element of the set of integers. So like I said, we'll define that in class a bit more formally. Okay, so either one of these is fine. They're equivalent to one another. Let's look at one more equation to solve while we're at it. So in this particular thing, we are going to need to do a little bit of manipulation. And what happens is we need to add these two things. So hopefully we have our identity cap on. Realizing that cosecant is 1 over sine. We now have a fraction being added to a non-fraction. So if I make this thing have a denominator of sine to add to add two fractions, I would have to do sine over sine to get this thing to have a denominator there. So now I have 2 sine squared x plus 1 over sine. Let's multiply both sides by sine x. Just want to make sure we have a clear separation between the two examples. And after multiplying both sides by sine, we have 2 sine squared plus 1 equals 0. Now we're going to subtract 1 and divide by 2. And I'm going to hold off right there. Think about that for a second. We have a sine squared equals a negative number. At this point, you can put the brakes on. There is no solution. Because when you go to take the square root, remember, this would be imaginary, and we're not going to get into, in the scope of this course, we're not going to get into imaginary numbers and that kind of thing in the confines of trigonometry. So in that case, we've got no solution, and in other cases, we had an infinite number of solutions. So lots of things can happen when it comes to solving trigonometric equations, and I look forward to talking about this more with you in class.